So welcome to the 11th annual Clean Air and Healthy Homes Program Symposium. So we have lots of people in the audience today, and we appreciate you coming to the University of Montana. To give you the official welcome to the University of Montana, I have Peggy Kurz, who is the Vice President for Integrated Communications.
Okay, thanks, Tony. What I did learn this morning is very important, which is you all got a goodie bag, and I did not. I think afterwards I'll be going up there to be able to join in the treats. Thanks again, and indeed, welcome to the University of Montana. I bring you greetings on behalf of our president, Royce Engstrom. He is literally on the road because I just spoke with him as he was driving between Lewistown and Great Falls. And I do know that if he was in town, he would be here. And he would probably spend the whole day with you because he's a chemist. He was a chemistry professor. And when we visit high schools, and last year we did a tour of the state, and in every high school I was in with him, if we happened to walk down the hallway and there was the chemistry lab, I couldn't get him out of it. So greetings on behalf of President Engstrom. We are so very glad to have you here on our campus for this day. We are here because we're excited about the opportunities and the wonderful discoveries that students are making, that our faculty are making, work that our staff is involved in. I did my undergraduate work years and years ago here, and after a lot of decades away, came back to the university. For some of you, I know you got up super early this morning, and this may be the very first time that you've been on this campus. And for others who live here in town, this may be one of just the next time that you've been here. And that doesn't matter, because what I would say is when you visit a campus of a university like here at UM, you visit a universe of things going on. I mean, I think university, I think universe. I think of all the various opportunities. So if you keep coming back to campus and only for the same things or seeing the same parts of campus and the same people, I challenge you to go to a different building, a different path, and meet somebody else or attend something different. In the world of science, it's just interesting to me how interconnected it is, frankly, with everything. We have the University of Montana commencement ceremonies on Saturday, and our keynote speaker was Ambassador Max Baucus, ambassador to China, after serving for a number of decades as the U.S. Senator, and then the senior U.S. Senator from the state of Montana. And he never mentioned the word science, but he certainly talked about it quite a bit in his lessons for the graduates as they move forward. He mentioned Libby and his effort over decades after meeting with people in Libby and looking at the health damages and health effects from asbestos and the mine up there. He talked about funding for not just research to find out what was going on, but research into health, and then research into how the federal government could help pay for health care for these diseases. He mentioned China in the context of global interaction and climate change and environmental, how the fact that everything is interconnected, and that he's now in China and he's looking at air pollution and what are the things that we need to do as countries, let alone the things as people. In his message, he was talking about interconnectedness and really, without saying science, saying we need to, as people, regardless of our careers, care about one another and care about our communities. We have students here who are studying life sciences. We have undergraduates who are doing research into brain diseases like Parkinson's or Alzheimer's, just two examples, or who are working with patients who have suffered loss of speech and learning that again, loss of hearing, or being able to move in some way again. We have students who are working in environmental sciences. And I know your real focus here is indoor and outdoor pollution. And I saw one of the posters of 2.5 PE, I know what that stands or actually, I remember that from some of my classes years ago. One of the things that is interesting to me is in this universe that we call a university, in my office, which is communications, news media, marketing, public relations. We know a fraction of what's going on, but this week I just happen to know about a number of scientists on this campus who are getting national attention in all kinds of different areas. So yesterday we had one of our bird scientists, and he normally works on songbirds, and actually the language that birds use is much more complex and in-depth, and those messages are much more varied than we realize, and they're taking apart the conversation of songbirds. He's also looking at an osprey nest that we have across the river on property owned by the university, and we are building a facility for our Missoula College. It's a 2-year college here at the university, and the osprey nest is very close to the construction project. And the builders have been working with the scientists, but the scientists were still wondering, will the osprey pair come back this year? Because they've been back every year, but now there's a lot of activity, noise going on very close to the nest. At one point they talked about moving it. They didn't. So there is a nest cam. More than 1 million people watch this osprey couple, Iris and Stanley as they're called, and they came back. Iris first, Stanley a little late. They have 3 eggs. And so he was talking with a group of visitors, giving them a tour of how he thinks this is one of the closest intersections of osprey nesting and major human activity going on with the construction site. And then also yesterday, I got a note from National Geographic magazine, which just posted a story by another scientist who isn't looking at birds, but is looking at cell structure and genetic structure. And in this particular case, he was looking at the genome and cell structure of insects called cicadas. And then I turned around and I know this week is a very big week for people in our astronomy and physics program because we are formally dedicating our newest telescope. We have a telescope on top of the Skaggs building here. In addition, we have one that's down on a mountaintop in Arizona. And I was trying to figure out a way to get there, and I never got the invitation. But if you think about someone who's a rower in a competition, and if she's rowing in a single scull, she can go so fast. But if you have 4 people all pulling in the same direction, they'll go faster. We're one of 4 telescopes that's on top of this mountain, and they're with the smaller telescopes all working together, get a larger magnification order and greater power. And what students now here are doing, and they're undergraduate students working with their teachers, they are looking for what are called exoplanets, which are very small, comparatively speaking, Earth-like planets that orbit around nearby stars. And the stars just happen to be in a zone that's considered habitable. In other words, they're looking for possible life on small planets nearby. And then finally this week, I know that there are some national experts coming to visit the labs of a research team that's working with biomarkers in the blood. Their area is TBI, or traumatic brain injury. And they've got preliminary results that are showing whether they'll be able to detect whether you had a concussion through a biomarker in the blood. In other words, detect it much sooner and be able to treat it much earlier. They're working with our Lady Grizz soccer players and also within on the football team. And those are just 4 examples going on right now this week that I know have received national and actually international attention because we monitor that kind of stuff. For me, science is about discovery. It's about seeing patterns and making new connections and discovering worlds that some of us aren't even aware are out there. And I know that this program, as Tony said, this is the 11th year. There are students who have come and sat where you are and then wound up working back in our labs as students at the university. There are students who've been here and have gone on to become engineers in their careers, and students who have gone on and are becoming physicians, medical doctors. I'm a longtime journalist, so that was my area. And I'm going to give you a couple bits of advice to close out. First of all, one of the things I know as a journalist is there are no stupid questions. So if today you're thinking about something and you don't quite get it, or you're wondering about something else, ask the question. Chances are there's somebody else in the room who's thinking the same thing and they just don't want to ask. So I invite you to ask questions, always. I also invite you to talk with someone you haven't met before. Find out what their passion is. It's a way to make new connections, and you never know where that will take you. But if you ask questions and you talk with people you've never met before, and then find out about something you've never thought about before. And then my final piece of advice is have fun. It's a wonderful world that you're doing today. I salute the work you've already done and with the poster sessions. And again, from the president and from all of us who work here at the university, welcome to UM, and I am with Go Grizz. Thanks so much.
So Peggy was also the dean of our School of Journalism for a long time. So any of those that are interested in the media or other things, she's the one to talk to.
Or writing about science, or doing videos about science.
There you go. All right, thank you, Peggy.
Fun.
All righty, here we go. So we are just going to give you a couple of housekeeping notes before we get started here. And the first thing is if there's anybody that needs a parking pass that doesn't have one, see Naomi back there, who is going to raise her hand right now. So anybody that has a poster that they haven't set up yet, the poster session is going on right now. And see Diana right there if you have a poster that needs to be set up in the back of the room. And also, if you, there's a couple of cameras that are in the room right now, so MCAT is right back in the back. So Ron, go ahead and raise your hand. So Ron is going to be filming this whole symposium, and then you'll be seeing people walk around with cameras too. So when you least expect it, smile at all times, because you just never know if you'll get your picture taken. Okay, so here's a quick run through of the agenda for today. So we have 10 presentations this morning. We're going to take a quick break at 11 o'clock, and then we'll finish it up with 9 presentations. We actually have a school in Alaska that's going to be joining us by Zoom at right at 11:15. And then we're going to take a quick lunch, come back in, do some evaluations, and then have some fun and give out some prizes for best presentations and best posters. So a little bit about the posters. I think there's anywhere from 12 to 15 posters out there right now. So judging begins at 9:45. At 11 o'clock, we're going to ask the people giving posters to go stand by their posters, and we'll make another announcement. And then you're going to have the poster judges that will interview you about your poster. And then at the end of the day, they're going to rank them first, second, and third prizes. And you see there, third, second, and first prizes are listed there, $50, $75, and $100 in gift cards. So the presentations, we have 19 presentations to get to this morning. They're 5 minutes each, 2 minutes for questions and answers. Right at 5 minutes, we're going to turn the lights on, and Jed Siren is right here, who is sitting where you guys sat 2 years ago when he was at Hellgate High School. So Jed is a former student and now working in a laboratory here at the University of Montana. As is Kyle Brester back there from Big Sky High School. And Kyle's been working with us, what were you, 3 years ago, sitting out in the audience, and now working with us here at the University of Montana now. So these two guys, former alumni from sitting out there, are helping us with the symposium today. Top 3 presentations will be awarded by your judging panel, which I'll introduce here shortly. $100 for third place, $125 for second, and $150 for first place. So let me go ahead and introduce the judging panel. So first off, we have Ben Schmidt. Go ahead and raise your hand, Ben. So Ben is air quality specialist for the Missoula City County Health Department and has been a judge for 9 years, something like that, a long time. So welcome, Ben, and it helps to clap because they're going to be judging your presentation. So second up is Aaron Yost, chief meteorologist for KPOP. Probably recognize her. So Welcome, Aaron. And Aaron was a judge a couple years ago, so welcome back. Ashley McGrath. So Ashley works for the Office of Public Instruction in Helena, the NAEP State Coordinator, former high school science teacher. So welcome, Ashley. Next up is Ian Foster. So Ian is a former middle school teacher. He's also on the board for the Montana Natural History Center, the Missoula Children in Nature, and Friends of Missoula Park. So welcome, Ian. And last but certainly not least is Mary French. Mary is a staff scientist for the Center for Environmental Sciences here at the University of Montana. I was a poster judge for a long time, and now she's in here as a presentation judge. So welcome to the judging panel. We have 19 presentations to get through, and it's go time. So the way it's going to work is I have a list of all the 19 presentations up here, and we are going to randomly select which one it's going to be. So if you see your name up here, if I start to pull up your presentation, then come down here as fast as you can, because we need to kind of get through all these pretty fast. And I will stop talking, and I'm going to load up a presentation. So before we get started, so I just want to introduce the school. So Big Sky High School. Who's out there from Big Sky?
Right here, just us.
Is that it?
We're all alone.
Come on, let's make some noise. So Big Sky High School. All right, Corvallis High School. Corvallis? All right, good. That's it? All right. Craigmont from Idaho. And Sentinel High School. Then Libby High School. Okay. And then we'll have Palmer High School from Alaska joining us remotely in just a little while. So, yeah, there you go. All right. So we'll go ahead and get started. All right.
All right. Ready?
Yep. 5 minutes.
Good morning, everyone. We're from Big Sky High School. My name's Nick Simmons.
And I'm Chance Mays.
Sam McKay. So our experiment is we tested radon around the school, testing to see if it was safe radon levels, and we compared these results to the results of the 2013-2014 Chem 2 class.
And the results that we were comparing were the radon tests that they conducted in their own homes. So our question was, do radon levels differ in various locations within Big Sky High School, and how do they compare to those of the students' homes tested?
So our hypothesis, so we expect to find the highest levels of radon recorded in the basement because that is closest to the source of radon. And we expect the radon levels at homes to be higher than the school levels.
I was just gonna explain that.
Okay.
And then basically just what radon is a radioactive gas found naturally in the environment. It is produced by the decay of uranium in soil, water, and rocks.
So the method of our experiment is what we did is we set up detectors in the following locations within our Big Sky High School. So we set up one in our chemistry teacher, Mr. Jones' room, the basketball room, which is above the cafeteria, so an upstairs location. The school basement below the men's bathroom, one of our teachers, Mrs. Helmer's room, and Mr. Moe's room, which is the classroom directly above the basement. So what we did is we set up radon detectors in these rooms and recorded 4 separate times for 48 hours to get 4 separate good data. And we compared these results to those of the houses from the Chem 2 students 2013-2014. There were 16 separate homes tested in 2013-2014.
And then just our variables. The graphs.
Okay.
So then our dependent variable is the amount of radon, and then the independent variable is the room the radon detector is placed in, the elevation differences with respect to the ground, the airflow in the room, and traffic in the room. So you want to talk about that?
Okay. So these are some of our graphs that we found. The top one is the mitigation foundation. So for foundation homes of basement in the from the data from the Chem 2 students. And as you can see, so it goes up to 16, and all these levels are below the EPA the EPA recommended level of 4 PCI. And so the mitigated systems working there in these homes, and they're very low. However, if you go down to the non-mitigated basement foundation homes, you see very high levels, some very unsafe. As you can see up there on the far right, there's that high of around 13, which is very, very unsafe. So these experiments actually really helped out some of these homeowners by detecting that their houses have very high radon, and they got their houses mitigated, which is actually very helpful for them.
So then we compared the homes in the basement levels and then homes without a basement. So we saw that the basement levels are close to the source, so we actually saw a lot higher radon levels when we tested the homes with downstairs. And then also the homes without basement, didn't have a basement, so they weren't mitigated, and those were also very high. So most of the living levels had higher radon.
These are the big sky radon levels, and as you can see, for the most part, very safe. The only level above the recommended EPA of 4 is in the basement, where we recorded one radon level of around 6. However, nobody's in this basement except the janitors, and the janitor allowing us to go on there. So the school turned out being very safe. One statistic that we're surprised with, if you can see Mr. Moe's room, which is right here. This room is right above the basement. So we
Actually above the reader we had.
Yeah.
Detectors.
So we expected this one to be higher than the rest of the school. However, it was the same as the rest of the school, so very safe.
So then our conclusion, as we predicted, the radon levels were highest in the basement of Big Sky High School due to its relativity and closeness to the source. And this was recorded at 5.6 picocuries per liter, which is above the national threshold for safe levels. And then the other locations with radon detectors recorded were well under the threshold and were at very safe levels. Mr. Moe's room included.
All right. Thank you.
Questions?
Any questions? Any questions at all?
I have a question.
Yes.
Were these all just one measurement, or did you do multiple measurements and these were combined?
Oh, so all those were averages.
Okay.
So yeah, we had, how many readings total? We did over a period of about
So
over 2 weeks.
it was 2 or 3 weeks, and we did 4 separate readings for each of those rooms.
Oh, okay.
And then the home data was from 16 separate homes in the 2013-2014 year.
And those were like self-reported by the students in their homes, so.
We used radon detectors given by our teacher, Mr. Jones.
But the schools were 4 different.
Yeah,
testings?
4 separate trials.
Why did you pick the rooms you did?
So what we wanted to do is we picked the one room, Mrs. Helmer's room, which is across our chemistry teacher's room, because we wanted to see a regular classroom, because in the chemistry room, the air is flowing differently than the other rooms. So we wanted to see the So we wanted to see the data in a room that wasn't a science room, and also we chose the Mr. Moe's room, which is directly above the basement, to see if there was higher radon above the basement than the other rooms throughout the school.
We wanted variation.
And then we picked one from the basement to where the radon is usually the highest, and one upstairs where you'd expect radon to be the lowest.
Did you place them close to the door in the rooms?
We tried to, we tried to keep them the same distance above the ground in all the rooms.
And it was on the back wall always, so far away from the door.
All right. Nice job.
Thank you.
Okay, we are from Corvallis High School, Mr. Hamill's chemistry class. I am Maddie Murray, this is Bella Pape, and this is DJ Pico. We tested the effect of spring sports on air quality, and our question was, how do various spring sports affect the air quality that the athletes and the fans are taking in?
So we hypothesize that the baseball fields will easily have the highest levels of PM 2.5, followed by the track, the tennis courts, and the cleanest air quality being the weight room. And we hypothesize that all of these facilities will have a higher rate of PM 2.5 than the 35 EPA health limit.
So we chose this because with spring holding the most outdoor sports in the Bitterroot Valley, most of our group members are involved in these sports, and we were just really curious to see what we are actually exposed to during our practices.
For our procedure, we set up the dialysis monitor and we tested the control for 30 minutes prior to or after each practice while running it during the practices. And afterwards, we recorded the possible factors that increased the PM 2.5 levels.
So what we came up with is we tested the weight room in our school, and our control was before our practice, and the average control was 207 micrograms per meters cubed. And then during practice, we found that the highest level of PM 2.5 was around 1,300, and the average was around 600, so it was pretty high in the weight room.
For the tennis courts, our highest PM 2.5 level was around 2,000 micrograms per meters cubed. And our average was around 330 micrograms per meters cubed, and our control average was about 125. And you can see here on the graph that during our practice, it got up to around 1,500. And then where they spike the highest is right when people are leaving the first practice and showing up to the next one. And you can see in between there too is our good control right there, and it never drops below the EPA health standard.
So then we tested the track, and our control was before practice, and those levels were about 483 on average, and then the highest level during practice was 899 micrograms per meter square cube. And the average level was around 600.
Finally, we tested the baseball fields, and from that, the practice, the highest PM 2.5 peak got up to 2,950 micrograms per meters cubed, but on average, it was around 871. But then after our practice, for our control, it got down to around 533.39 micrograms per meters cubed, which was still above the EPA health limit.
So this is a comparison of all of the tests we ran, and you can easily see that the baseball fields has the highest average, and the tennis courts being the lowest average, but all of them are always above the EPA health limit.
For our contributing factors, the baseball fields, the dialysis monitor was placed in the dugout, and so people were coming in and out, and it was on a windy day, and there's a dirt infield, and so that also contributed to it, as well as our baseball field is placed next to a dirt road. The track was at the finish line, and there was interval practice. It was a windy day, there was a lot of people running, and it's also by a dirt road. The tennis courts is by a dirt road, there was cars leaving and arriving, 2 practices, and on a windy day, and it was placed on the court. And then the weight room was indoor at the weight room. In the entrance, there was a small room, lots of people going in and out, and weights were being dropped. So as we had hypothesized, the baseball fields had the highest levels of PM 2.5. Following this was the track and then the weight room. The Corvallis Sport Facility with the best air quality was the tennis courts, and all 4 were above the EPA health limit.
So what we could have done better to improve this was we could have ran multiple tests on different days as well as in different areas. Our tests could have been during the same time of day, and we could have ran longer control periods.
Any questions?
Question. If you guys were to
have done this in the fall, which sports do you guys have in the fall that you could have
Um,
researched?
We could have done soccer, cross country, football,
Volleyball?
and volleyball.
Okay. How do you think that would have compared? Think it would have been different or any?
I think it would have been different.
Yeah, I feel like being in this fall in Montana, we had a lot of forest fires, and so that might have still affected it if it was earlier on in the season. However, later on in the season, I guess we don't really know, but that would have been a good time to test. Thank you.
Did you check the monitor that you're using in any way to see if it was accurate compared to any other devices? The reason I'm asking is during the forest fire event, we can barely see a couple blocks. It usually reads around 500 to 600 micrograms per cubic meter, and a dirt road will typically put up coarse material that's between 2.5 and 10, and will have very little impact typically on a PM 2.5 monitor. And so that's why I'm just wondering about the values. And for instance, there's a monitor in Hamilton. Was there any comparison with that ambient monitor?
You know, we actually didn't test with a different monitor, but we really should have. That would have, we could have seen if our results were completely accurate or not. And we did not look at the Hamilton monitor as well. But that would have been really good idea. Yes.
Are your data numbers there, are those coming directly off the dialysis monitor? Or you run a little conversion that converts them into the micrograms per cubic meter?
Yes, we did convert that.
Those are completely right?
Thank you.
All right, thank you.
Hi, my name is Rachel Rebo. And I'm Haley Craig, and our project is on the effects of indoor PM 2.5 on the respiratory health of people with asbestos-related disease. We're from Libby High School, and our teacher is Mr. Gene Rick.
So before I get started on our project, for those of you who don't know the asbestos situation in Libby, I'd like to give you a quick background. Presented in this picture is Libby's old vermiculite mine, which is located roughly 6 miles east of Libby. The mine began processing vermiculite in 1919, using it in insulation and in soil treatment materials. However, vermiculite contained an unusable contaminant called asbestos. Miners were heavily exposed to asbestos, thus they exposed their families and people all over the community. As you can see in the upper left-hand corner, asbestos is a thin, narrow fiber that can easily make its way down into the air sacs of the lungs. This caused 2 major lung problems. In the picture on the left, this person has no asbestos-related disease. However, in the picture on the right, this person is diagnosed with asbestos-related disease. They have fibrosis of the lungs, which is scar tissue that fills up the air sacs in the lungs, and also a pleural plaque forms between the rib cage and the lungs.
Our question was whether or not higher levels of indoor PM 2.5 made breathing harder for those diagnosed with asbestos-related disease. We hypothesized that as PM levels increased, it would be harder for those diagnosed with asbestos-related disease to breathe.
We began our project by placing a dust track monitor in the home for 24 hours in an open area to get a good feeling of the home. We also attempted to place the monitor at least 10 feet away from any ventilation or fireplace or door. We gave each participant a questionnaire asking if they have asthma or if they smoke, if they spend time outdoors in the winter, and if they are currently taking any medication. In the picture on the right is a peak flow meter that was given to each participant. They would take a deep breath in, and then they would blow as hard as they could into it. They blew into it for twice a day for 3 days. For those 3 days, they recorded the date it was taken, the time it was taken, and the reading for that specific time and date.
Okay. On the graph on the right, you can see our average lung capacity relating to PM 2.5 levels. The x-axis shows PM 2.5 levels measured in micrograms per cubic meter. On the y-axis, you have lung capacity measured in liters per minute. The line of fit shown here shows a slope of almost 0. The 0.95% on the left of increased lung capacity was found by averaging all 18 participants' slopes and dividing by the range in lung capacity. The cluster of points both above and below the line of fit lead us to believe that there were other factors involved with our experiment, since common sense tells us that lung capacity can't increase as PM 2.5 levels increase. We concluded that we did not have a large enough sample size to support our hypothesis. If we were to do this project again in the future, we would have a much larger sample size to gather more significant data. We would have a longer test period for perhaps a week, and we would increase the frequency of the breathing tests for maybe a 12-hour period from 9 a.m. to 9 p.m.
We would also have each participant record activity in the home, whether it be cooking or cleaning, or if they had guests over and if those guests smoke. We would also position the monitor in the same spot in the home and also measure exactly where the monitor was placed. And then we would have each participant record the time they spent outside, how long they spent outside for, and what kinds of activities they were doing outside. Thank you. Do you have any questions?
One thing we really like to do is encourage questions from other students. So who wants to ask a first question and you get an extra goldfish? Come on. All right.
So the people you used to take the lung capacity sample, were they all relatively of the same age, or did they vary?
We didn't do anybody in like 13s. These were people who had asbestos-related disease, so they've lived in Libya for a long time, so they're all roughly the same age.
Okay.
Yes.
How did you get a list of the cohort of people who have the disease?
We started with my dad, who is diagnosed, and it was just a connection from there. He knew people, they knew people, and that's how we got all of them.
Can I ask again, how many people?
18.
No.
We have time for one last question.
Did they all the people that you tested, did they have approximately the same severity of asbestos-related disease or the same disease?
That I don't know. I'm sure that some of them had different levels of it, but we didn't ask them how severe it was.
Okay, thank you.
Hello everyone, I'm Jeff Quackenbush. And I'm Avery Flynn. We're from Sentinel High School. We're in K-2 and our instructor is Mr. Taylor. And our project is, how does activity in the Sentinel High School weight room affect the PM 2.5 levels? So yeah, as you just said, our project was testing the amount of PM 2.5 particulates in the weight room as caused by activity. A little bit of background. Studies have found dust and other airborne particulates get in the respiratory system and they cause health problems. Also, particulates and like chemicals released by cleaning products, furniture and paint are also commonly found in weight rooms. One of those is formaldehyde, and we found formaldehyde is very dangerous and causes cell carcinomas in the nasal cavity.
All right, so we hypothesized that, actually first I should explain. We have periods during the day in the weight room. Monday, Tuesday, and Friday are the normal class period days, periods 1 through 7. Wednesday and Thursday are block periods. Wednesday is odd classes, 1, 3, 5, 7, and Thursday is 2, 4, 6 are even classes. Thursday has no weight room classes other than zero period, which occurs every day at the beginning, before the beginning of the school. So we hypothesized that since Wednesday has classes every single period, including weightlifting, including zero period, we expected that it was going to have the highest concentration of PM 2.5 levels.
For our method, we use a Dylos DC 1700 air quality monitor. And our teacher has 2 of those, and we alternate between to make sure that we're getting the same readings. We place it in the weight room 15 minutes before zero period starts to establish a baseline, and then we let it running throughout the day. And we also we tested on a Monday so that the air room or the weight room could clear out over the weekend, and we could have a more clear baseline.
All right. So as you can tell from the data, this huge spike right here, that is around zero period, and it jumped up to about 14 micrograms per cubic meter. And it started to drop a little bit as the day progressed, and then it pretty much just stayed constant throughout the rest of the day. On Wednesday, it also spiked fairly high at zero period, declined a little bit, and right there, that little second spike is first period, and then this last really big spike at around 21,000 seconds, which is like, I don't know, like 1 o'clock. That's like 5th period, 7th period, and that had the largest. For Thursday, it spiked up fairly high, right at zero period, and then dropped dramatically and stayed like that for the rest of the day.
So for our results, we performed a NOVA test, which measures the average, the mean PM 2.5 level over the course of the day. And then we performed t-tests after we found significant differences in the means. And the t-test compares the means of each day to each other to see which day had the highest PM 2.5 level.
So our conclusion was that Wednesday did have the highest PM 2.5 over the course of the day. Thursday also had the highest peak, and Monday reached a fairly steady level. Okay, possible errors. The testers, us, we were not in the weight room the entire day, so we could not tell if someone was tampering with the monitors or altering it or anything like that. And it is possible that each day there's different exercises, lower body, upper body, core, all that stuff, that may have an effect on the amount of work that people are doing, so they may be sweating a whole bunch, so that has an effect on the PM 2.5, maybe. And those are sources. Any questions?
You said you alternated between monitors?
Yes.
So how many different days is this? Is this just one Monday, one Wednesday, one Thursday?
Well, we put the particular times in there on 3 separate Mondays, and we found that they were pretty much the same every time. So we didn't test the Wednesday and Thursday block days multiple times. But after we had established that each day was pretty consistent, we tested the Monday, we tested the Wednesday with high activity, and Thursday with low activity.
Okay. So these are all just one day, they're not averages over 3 days? They're just one day testing?
They're just one day.
Just so I'm clear on the alternating between particulate detectors, you said you used 2?
Yes.
Can you explain how you alternated, or?
When we did the Monday test, we used one of them the first time and the second one the other time, and then we went back to the first one and we just found that they were pretty consistently recording the same data. So.
Now, you mentioned the formaldehyde at the beginning, just out of curiosity from your research, what would be the sources in an older building of the formaldehyde in a way?
Well, like the rubber mats that are on the floor, there's those, and then we have platforms that are wood, and then they have rubber on the sides to catch the weights. Those all contain formaldehyde.
Okay, so
especially in a weight room where you're breathing heavily and inhaling more out in your lungs and stuff. That's what our concerns were.
So how often are the mats replaced in the weight room? I know it's a little off topic from what you're looking at.
I know we had some donors and we kind of like redid the weight room, I think 4 years ago. I would assume they were replaced then. I would assume they haven't been replaced since then.
Yeah, I'm just curious because the half-life of formaldehyde in the materials, you know, particle board, et cetera, the mass, number one, they've reduced in the manufacturing process the aldehyde contents considerably. But it'd be real interesting just to know, well, what is the formaldehyde in a enclosed space like that? For, you know, 4 years later or 1 year later, that's
Hello, my name is Claire Bonesock.
And I'm Austin Bonesock, and we did the relationship between aerobic recovery time and PM 2.5 levels in asthmatics and non-asthmatics. We go to Sentinel High School and are in Chemistry 2, taught by Brett Taylor. So our question was, does an increase in PM 2.5 air particulates affect an asthmatic athlete's aerobic recovery time more than an athlete without asthma? And we chose this because me and one of her best friends have asthma, and we wanted to see if we were affected more than anyone else.
So for background information, our research showed that asthmatics have more difficulty performing the STEP test, which is a test performed by wildland firefighters to measure their fitness level. So we know that it's a good test to use under aerobic stress than non-asthmatics. And then the purpose of our project is to see if increasing particulate levels affect asthmatics' aerobic recovery time more than non-asthmatics.
So for our hypothesis, we said all subjects with a longer aerobic recovery time and lower vital lung capacity with higher levels of PM 2.5 air particulates. However, the asthmatics will have longer recovery times and lower vital lung capacities than the non-asthmatics.
So for measuring the PM 2.5 levels, we used a Dylos DC 1700 air quality monitor. And we needed a respirometer to measure vital lung capacity, so we used a Voldine 5000. For our step block, we used a 32 centimeter block. We had 2 subjects with asthma, male and female, 2 subjects without asthma, male and female. They were both around the same age and same fitness level, so we didn't have differing, And then our variables were the air particulate levels, the exercise parameters, and the vital lung capacity. And the vital lung capacity is the forced air into your lungs.
For our experimental procedure, we started out measuring a resting pulse rate for everyone, and then we'd use a respirometer to measure their vital lung capacity. And then using a metronome with a pace of 60 steps per minute, we'd have them do the step test for 5 minutes. And then again, after the activity, we'd have them use the respirometer to see how much lung capacity they had afterwards. And then we'd time them to get back to their resting pulse rate. And then we'd repeat this with high and low PM 2.5 levels.
So while we performed the test, we did on 2 different days. This date's data is from May 4th on a Monday before zero period. So this is the time we were in the weight room, and this before zero period was in there for the low particulate levels. And then this was on a Thursday after the highest day, according to Jeff and Avery's data. The PM 2.5 levels were about 3 times higher than on our low day. We were in there about here-ish. And then, so this is our subject, or our data from our subjects. As you can see, the non-asthmatic male had higher lung capacity than the asthmatic male, and same with the non-asthmatic female and the asthmatic female. The same for our high day, the non-asthmatics had higher lung capacity levels. However, their starting lung capacity value dropped on the high day. And then we measured the aerobic recovery time. So on the low day, the non-asthmatics, well, the male had a longer recovery time than the non-male, and the asthmatic female had a longer recovery time than the non-asthmatic female. So our data was really inconclusive regarding the recovery time. So our data really did not support our hypothesis, and the particulate levels did affect the lung capacity, though. Any questions?
your subjects have comparable fitness levels, even though it was non-asthmatic versus asthmatic, where you
Yeah.
have similar fitness?
We're all athletes in season right now, so it's pretty close fitness levels.
Do you think having more subjects would have changed your outcome?
I think it would have, because there would have been like more data to look at instead of 4 of us.
Did you track the heart rates as they decreased, or were you just waiting particularly for them to get down to the resting heart rate?
We had them sitting there, not moving, and we had them timing, so they were holding the pulse until it got back, and they just restarted every minute. So yeah, they were constantly tracking it. Okay, thank you.
Hi, I'm Jessica Miller.
And I'm Cassie Enninga.
And our project is on the effects of soil type on levels of radon accumulation. We are from Libby High School, and our teacher is Mr. Gene Recken.
Does soil type have an effect on radon emission and accumulation? This question was tested before by 2 Libby students 2 years ago. They put the monitor in the home, and we wanted to eliminate the variables of the home. Ventilation and the foundation and tightness of construction of the home may have affected our experiment, and also if someone uses the basement door.
How does radon travel through soil? Radon, a gaseous product of the breakdown of uranium, travels through the spaces between the soil particles and gathered in the container we used, resulting in different readings for each soil type. Both 101 and 103 are more compacted soils due to their small particle and pore size, and 303 is a more aerated soil because it has larger particles and pores.
The hypothesis we were testing was soil types that have coarser and contain more airspace will release more radon than soil that is more refined, sandy, and compact. To set up, we covered the edges of our container so they wouldn't have an airspace, so we wouldn't get any airflow that would change our readings.
We used green plastic containers like this one to collect the samples. Each container was placed outside at each testing site and left there for a week before being moved to the next site. Inside each container was a Pro Series 3 radon gas detector, which gave us a reading when the test period was over.
The Kootenai River is here, the W. The floodplain area is where we tested 303. In town of Libby, we tested soil type 103, and Libby Creek flows down from the Kootenai River, and on the bench of Libby Creek, we tested soil type 101.
This graph shows our results for the 3 soil types we tested. For 101, we got readings of 1.6 and 0.7, our best readings since they were the lowest. 103 gave readings of 1.8 and 1.7, and 303 yielded readings of 5.8 and 4.2. When our results were compared, it was discovered that 303 had the highest readings. It is the coarsest, most aerated soil of the 3 tested, and so supported our hypothesis.
When we first began our experiment, we used a wooden box that we created to simulate the home. So it had sheetrock, insulation, and house paint. We had to change our container because we were getting electrical errors, and we also suspected that we were getting humidity and temperature problems as well.
Our sample size was not big enough on each soil type, and we also could have tested more soil types with different pore sizes to better support our hypothesis or not support it.
Any questions? Yes.
How did changing your containers potentially get rid of your temperature and humidity issues?
The wooden box didn't allow for any how do I say this?
Just temperature to escape. It was insulated, so if it heated up, it stayed really hot, and the monitors had to be between a certain temperature. Yeah, we had temperature readings of like 103 in our first box, so.
I found one of these back here. Looking for a home. All right, got it back. All right, you ready? Oh, look out. All right, go ahead. You gotta ask a question, though. That's part of the deal.
I was wondering if you had more options available for the soil testing types.
We did, but we had some difficulty finding similar soil types, and by the time we could have tested, we were out of time, so.
Well, also you had a power source. You had to get a power source to your monitor, so you had to know someone who owned the land. So you had to have a power source. There had to be a house on the soil type. So you had to know them because it's a school activity.
Yes.
So you guys said you recorded for 1 week straight, right?
Yes.
So did you just leave the monitors outside underneath the things while you were recording?
Yes.
Do you think the fact that you protected that specific spot of soil from outside elements could have affected your results?
Well, it could have, but in order to get an accurate result, we had to protect the monitor from outside elements.
We didn't want the variables of different outside elements. Oh.
All right, thank you.
So we did our air quality project at Lost Trail. I'm Zena Smith and this is Kira Doyle, and we're from Corvallis High School, and Mr. Hamill is our teacher. So our question was, how bad is the air quality at Lost Trail in different locations? Our hypothesis is that it would be near the 35 EPA standard in the rental shop because of the waxing and stuff that goes on in there. And then it would be above the standard in the kitchen because of the cooking and the smoke that escapes out of the chimney. The ski school would be fairly low because not much is going on there. For our procedure, we tested in 4 different locations: outside, in the ski school, in the rental shop, and in the kitchen. In the ski school, we put it in the back room away from the propane heater because we did not want it to get melted. In the rental shop, we put it on the tuning table away, near where they wax the skis, and so it would pick up those particles. In the upstairs kitchen, we placed it in between the fire and the kitchen so that it would pick up not only the cooking but the escaped smoke from the chimney.
So in the upstairs kitchen, it was like we thought it was pretty high, and as it got later and closer to lunchtime, it went up because they were cooking more for lunch. The ski school, like we thought, it was pretty low, and it went down as it got later as the ski instructors left to go teach their classes. The rental shop was a lot higher than we thought it would be, and probably from waxing skis. And then outside was our control, and it was very low and consistent.
We used the outside as our control group because we figured that it would be a steady line because of the snow taking the small particles out of the air and it being outside in the fresh air.
Okay, so the whole day, you can see the kitchen was very high, the skate school was low, and the rental shop was very high too, and outside was the lowest. So the rental shop and kitchen were both very high, but the rental shop was a lot higher than we thought it would be, and the ski school was low. So improvements, we could have tested a longer time at each location and done testing over multiple days. Questions?
Why was the length of your testing periods different than each location?
Because I work up at Lost Trail, I had lessons throughout the day, so I had to change them at different periods of time.
Did you guys just test one day?
Yeah, we tested throughout one day. Yeah. Yes.
Was the day you tested fairly busy, or when did you test it?
We tested it towards the end of the season, and it was a fairly normal day. So.
Any more? All right, good job.
Hello everyone, my name is Isaac Jones.
And I'm Ari Benefield, and we are from Movie High School, and our teacher is Mr. Gene Logan. Our experiment was radon mitigation barriers in basements and crawl spaces.
So our question, we were trying to find which material would mitigate the most radon in our miniature house that we built. The traditional materials that are used in mitigating radon are concrete and plastic. The materials we used were concrete, rubber roofing, sheet metal, tar paper, and plastic, just because they are normal construction materials that are used and are easily accessible. We didn't really have a hypothesis, we just conducted an experimental test. There was no really reason to believe that one material would do better than the other one, so it was more of just a test than it was a hypothesis.
So in our miniature house that we built, it had traditional materials with studded walls, insulation, had sheetrock and paint on it. This is the bottom floor that comes down, and this is the top floor that comes on top of it. And this is the box put together completely. We did this like this because we wanted to eliminate any variables of varying houses. So.
Our procedure, we had to put the box in a greenhouse because of temperature and moisture conditions. The monitors they read at above 32 degrees, and it was during the winter, so we put it in the greenhouse to eliminate that. We used two monitors. We put one in the bottom floor, as you see on the left there, and then one on the top floor, as you see on the right. And we did a weekly test, so stayed in there for 7 days, and we used sandbags around the outside just to keep the radon inside the box so it didn't escape and change our readings.
So here are our results. This is, on the bottom is the mitigation materials that we used. And this is our control experiment with zero any kind of material underneath of it. This is concrete, rubber roofing, tar paper, plastic, and sheet metal. And as the results show, that concrete did the best with mitigation.
So this is our cost effectiveness that we also did. We researched what the prices of each material were.
As you can see, concrete did the best, but it was also one of the most expensive ones. So if your reading in your house isn't very high, then there's no reason to use something that's very expensive. So like say you have a reading of 10 picocuries, you could just use plastic to get rid of 60% to get to the accepted value of 4 picocuries, and it's only 14 cents per square foot. So it'd be more cost effective. As also part of our conclusion, we have our sources of error. We didn't do enough trials. We only tested each material once due to time. And we also, the materials had difference in thicknesses between concrete and the plastic. So we should have used more trials and had a baseline thickness. The stack effect wasn't part of our experiment. It's kind of interesting. The stack effect is when the ground is frozen, the only place for the radon to go is underneath the house. So it creates higher readings. So when the ground wasn't frozen, we had 1.6 picocuries and 8.1 picocuries. It's kind of interesting to see the difference. Any questions? We did 2 floors to simulate more of a house as a basement and the living quarters, and just to show the 2 different readings that you would get in a house.
So in your house, were the walls made of all the materials, or how did you measure each material differently? You said you wanted to measure each individual material for the.
Yeah, the materials were laid on the ground, and then the box was folded down on top of it. So there was no difference in the box at all.
Was there anything between the 2 floors of the box to stop the radon from escaping there?
Just a piece of 1/4-inch plywood that you would have in a normal house.
Oh, there's a comment and a question. I think your hypothesis, you actually had one, which was all materials are going to behave similarly. It's a good hypothesis. But
okay.
Yeah, one thing I have a question about is how long would each of those in house construction, how long would each of those materials hold up? How long would each one be an effective barrier?
Yeah, that's very true. Like concrete is it would last a lot longer. So I mean, like I said, though, with the cost, it is more expensive. So you just kind of have to weigh your odds out, I guess. So.
How did you choose the location on these tests?
Like I said, we had to put it in the greenhouse. It was at our teacher's house. So just to keep from the difference in temperature. So. Any other questions?
The radon source, where's the radon actually
I don't know. The stack effect, like I said, we did in the winter, so the readings were a lot higher. So that kind of gave us a difference there.
You just had like soil or rocks?
Oh yeah, it was rocks. It was, I think 4 feet of like big 2-inch rocks that were in the greenhouse.
All right, hi, my name is Ben Tabaracci. I'm Cody Mediela.
Walker K.
And I'm Ryan Mason. We're in Mr. Taylor's Chemistry 2 class at Sentinel High School, and our project was about air quality in indoor swimming facilities. Our question was, how does activity level in swimming pools affect air quality?
And PM 2.5 is particulate matter that is less than 2.5 micrometers in diameter, and they can cause respiratory tract inflammation and minor health problems.
And the reason that we chose this project is I've been a competitive swimmer for the past 9 years, and I've personally experienced or witnessed several athletes get asthma attacks and different respiratory issues during both swim meets and practices. And because of these experiences, we are hypothesizing that with increased activity in pools, that the PM 2.5 level will rise to a level that will impact your lung capabilities.
So for the procedure, we used a Dylos DC 1700 air quality monitor, and we obtained permission from local pools in the Missoula area, and then we placed the air monitor 5 to 10 meters away from the edge of the pool, down low, because that's where the activity is in the pool. And then we used that, we left it over for 24 hours, and then we took it back to our school, and then use Microsoft Excel for the graphs. And then this is out of the Dylos handbook, and then they do particles per cubic foot divided by 100, and our graphs show just particles per cubic foot.
Okay, so for the first pool, we didn't list what the actual pool name was for confidentiality reasons, but basically what we were doing is we would take a baseline sample from overnight, so we were comparing each pool to itself. And then, so we took a sample from there, and then practice started at 5:30 in the morning, because swimmers are crazy. And we took all of our sample from there, did a statistical test on that. We also were testing large particles. It's a little more obvious on the spike that occurred. And this is our statistical analysis for our first test.
Okay, so we ran a two-sample t-test, and for the first pool, we came out with about a mean of 48,000 particulate, and we also created a 95% confidence interval because we weren't able to do multiple tests on different days because I got nervous about the electrical and stuff like that. So if we ran this test hundreds and hundreds of times, 95% of the means that we would get would fall in our 95% confidence interval. So in this one, we had about 38,000 to 60,000.
And then we tested another pool, pretty similar results. We took the same baseline overnight. We have a spike at about midnight, and we asked about that. That was because of a cleaning crew that came in. So we took it before then to make sure that didn't skew our data. Took the same time period from 5:30 to 7 in the morning during our practice time. And when we were talking about what these particles were, they're chloramates, so the chlorine will bond to waste from swimmers, and that was getting suspended in the air. This is the large particle from pool B.
Okay, so the same thing for pool B. You can see that our mean was a little bit higher, about 92,000, which still stays in about the fair air quality range. When we actually ran our actual t-test, you can see our p-value is well below our alpha level of 0.05. And the confidence interval for this one's about 87,000 to 98,000.
And then finally, we tested during a swim meet because being a competitive swimmer, I've witnessed multiple asthma attacks that occurred during swim meets, so we were interested in this. And as you can see, we had a huge spike. It actually got above 700,000, which was well above the hazardous level. So we did same thing, baseline, and then compared to the actual meet. Same spike is seen in a large particle.
Again, same thing, except this one was way higher. So that was just our mean was about 269,000. But like Ryan said, it spiked up to well over 700,000, which, if you remember back to the little table, is more than twice the actual level for very poor air quality.
In our conclusion, we supported our hypothesis that as activity level in pools increase, so will the PM2.5 particle levels.
Okay, so mitigation, we noticed when we were in the pools that all the ventilation systems are on the ceiling, and most of the actual heavier particles that cause inflammation in the respiratory tract are more towards the ground level, so if the fans were more towards the ground level, that would help. And then having an air quality sensor that would kick in extra fans at around about 100,000 particles per cubic foot would be really helpful.
And then references, and does anybody have any questions?
So your units of measure were particles per cubic foot. Do you have any information how to correlate that to micrograms of weight per cubic meter?
I do not. We were basing it all on the handbook that came in the air quality sensor that we're using. So we based everything on the standards that they were giving, which was the picture that we had early on.
Okay.
But I cannot compare it to the EPA standards.
Right, yeah, okay. The weights, the particle numbers are usually not easy to correlate, so.
Yeah. Okay. Thank you.
Nice job.
It's over there.
We're going to go ahead and get started. So we have 3 presentations from Palmer, Alaska, which is just north of Anchorage. And they're going to do back-to-back-to-back presentations. So, Cheryl, are you there? Can you hear us?
Wait, I've got them on mute.
Can you hear us? What about you guys? Say something.
We can't hear you, Cheryl. Oh, wait. There we go, we got you. Okay.
All right, we hear you. So we're gonna, you have 5 minutes for your talks and then a couple of minutes for questions and answers, and we have a lot of people from Western Montana and Idaho in the room here. So welcome to the symposium and take it away.
Hi, we're Palmer High School, and our hypothesis is if students attend Palmer High, then they're at a high risk of facing the health problems associated with radon.
Radon is a chemical element, it's radioactive, colorless, odorless, tasteless. In a lab, its purpose is initiating and influencing chemical reactions, and is used in some spot treatment and safe amounts.
Can you guys hang on just one sec? What is this?
Yeah.
I don't know where that feedback's coming from. Does anyone know on my computer? Okay, go ahead.
Okay, where does radon come from? Radon gas is continuously released by uranium and thorium-bearing rocks underground deep beneath the Earth's surface. What starts is the rocks start to decay naturally, and then this gas emits from it, and then it moves upward through the soil and into homes and other things.
Radon has no short-term effects, but it is the second leading cause of lung cancer in the U.S. next to smoking tobacco. And smokers in places with high radon have a very extreme risk. These easily get trapped in the lungs, especially the organ. 15 to 20,000 people die every year from infected water, and it causes around 19 stomach cancer deaths per year.
Okay, so our experiment, the experiment that we did was we had radon detectors, and we set up 3 locations around the computer and room and boiler room. They're all on the same floor, which is the lowest level of the school. And we tested them for around 3 days, and we took the readings. The map at the bottom of the screen, that's Alaska, for people who don't know what Alaska looks like. The yellow zones are safer zones. The darker the colors get, the more dangerous those radon levels are. So we are, I don't know if you guys can see it's really far away, but the Matsu borough is an orange zone, which means it's between 2 and 4 PCIs per liter, which isn't bad, but it's not necessarily good.
The lowest leaking chemical there was the boiler room, which is surprising, and the highest was in the band room at a 4.4. The band room was at a level 1, the theater was at a level 2, and the boiler room was at a level 3.
Okay, so exposure. What we really wanted to know was, are students at risk of lung cancer if they're hanging out at the lower level of the school? And the answer we found was no, they're not. The levels that we picked up on the detector weren't past the 7 PCI per liter safety limit. So we weren't in danger, but the readings we got were still pretty high. Well, they weren't 0, so, and schools might consider maybe moving larger classes or popular places in the school to higher altitudes, further from the ground, further away from radon. Okay, minimizing radon exposure. Radon seeps through the foundation cracks and other openings of your home. It's a gas, so it's really easy to get in between all those tiny little spaces in your house. You should consider using radon reducing procedures if the radon level in your home exceeds 4. Ways to fix the problem: you could hire a specialist, because radon is really complicated, and these people have been to college and gotten degrees in how to stop this gas from giving you lung cancer. You should attempt to fix any large cracks and holes in your home, although that isn't the safest because it's gas and it can still get through. And this is kind of a myth, more than an actual fact, that some people like to air out the lower levels of their homes to get the gas back outside. There is one system called the active storm depressurization system, and it's a device that can physically extract the radon gas from the ground before it actually rises into your house, and it costs around $2 to $6 per month, which is actually really cheap. Might be worth investing in.
Areas of error or in future experiments, there could have been some inaccurate results, possible tampering with equipment, unmonitored experiment, and then for future experiments, P5, CO, radon levels in different areas in different buildings, just things to think about.
Citations. Okay.
All right, thank you.
Okay, we got time for one or two questions.
Questions, guys?
How old is your school? In your hypothesis, you seem pretty concerned that Palmer High School was the problem. Is this an older building or a newer building? What's construction like?
Palmer High was built in about 1975. This is Garth Morgan, assistant principal here. Built about 1975, so that would put us at 40.
Palmer High School is 40 years old.
Okay, great job. Thank you.
Hi David, thanks for coming. I don't know if we're getting it. I just turned this off.
All right, Dominique.
Hi, hold on.
All right, whenever you're ready.
Hi, my name is Dominique Hines and I'm from Palmer High School. I'm a sophomore. I decided to do my project on the effects of carbon monoxide levels with burning paper and plastic. My hypothesis was that our group thought that the levels with CO would rise above the levels with paper, but nothing to the extreme of what we found. So, some background information. Carbon monoxide is a poisonous, odorless gas resulting from the incomplete burning of natural gases. 170 people die each year from carbon monoxide poisoning. It displaces oxygen in the heart, in the brain, in the blood, and deprives your heart and brain. It also causes you to suffocate and lose consciousness. It can cause headaches, fatigue, and dizziness. Carbon monoxide is found anytime you burn fuel, stove, lanterns, grills, fireplaces, and furnaces. I chose to do my presentation on carbon monoxide because it often goes unnoticed and is very harmful. And I always heard that you never want to burn plastic in a fire, and I wanted to know how much it actually affects the environment and yourselves. Some of my variables, my independent variables were paper and plastic, and my dependent were the CO2 levels. My controls were the fire. We used the same size fire pit and about the same size fire to test both the paper and plastic, and all in the same place, about the same time of day. My procedure, we went onto the view, we went on the view, like at the bottom, and we made a small fire that took about 15 minutes to get going. And then we put about like a medium-sized paper in the fire for about 5 minutes. And then after that was burned, we put the plastic in for about 5 minutes, and all the time we were holding the carbon monoxide over the fire, and we recorded the time and then gave the machine back to Ms. Williams. This is just some of my data, some of the things we observed when we were testing. The weather was calm, it wasn't windy or anything. We did it outside. It smelled awful, like burning rubber. And that's about it. This is my data. So the first spike is when we were burning paper, and then when it spiked above the line right there, that's when we burned plastic. And the line is when carbon monoxide starts to get dangerous. And so you can obviously see that it spiked up way above what is safe. My summary is when the paper was burned, the levels remained low, like healthy. And when the plastic was burned, it wasn't safe. And the paper didn't really increase the levels of CO that much. We concluded that, basically, burning plastic is extremely dangerous to the environment and to anyone around, especially in large quantities. We could test this to prove it more, but it's extremely unsafe to burn plastic than it is paper. Some of our areas of error and improvement, we could have tested more plastic for the fire or more paper multiple times. And we should have gone to different places and tested and made different fires. We did notice too that it could be a contributing factor because obviously wood gets made into paper. So that could have affected our data just a little too. And that's about it. And this is my own work. And now our thanks.
All right, questions for Dominique? In the back?
Did you repeat that?
What type of plastic was it? Was it like a bag or something?
No, it was a plastic container, something that you would pull something that you bought from a store out of, it's just like something you get an electronic out of a store. Plastic wrap.
Got time for one more question.
I have a question, but I don't want to focus.
Okay.
But go into the mic.
Amount of Rice Krispie treats. Anybody want to ask?
One more question, Dominique.
Okay.
Okay.
So you said the type of plastic was just something that you would get maybe an electronic out of, or something that sounds like a pretty thick plastic. What do you think would happen if you use different types of plastic? I know in recycling, a lot of the plastics have different numbers associated with them. Do you think that would have proved to have different results if you used 1, 2, 3, 4, or did you consider using a plastic bag versus a plastic water bottle, et cetera?
We did not consider doing that or even take that into consideration. But definitely, if we were going to do something in the future, we would probably do that with larger pieces of plastic and different kinds too. But it would probably affect it, especially the quantity of it. But no, we didn't do anything like that.
Thank you.
All right, thank you.
Thank you.
All right.
Yeah, whenever you're ready, go ahead.
All right. My name is Sean Smith, and I was doing my tests on radon gases, especially in households that have both a basement and a crawl space. And my hypothesis was to see if the sort of levels of radon that varied between the distance of the basement and the crawl space. What is radon? Radon is a radioactive, colorless, tasteless, odorless, noble gas occurring naturally as an indirect decay product of uranium and thorium. How can radon hurt you? Radon levels become dangerous at 4 pCIL. Radon gas is one of the leading causes of lung cancer and is reported to be responsible for over 20,000 lung cancer-related deaths each year in the United States alone. Levels of radon gas and their risk. Comparative risk chart of radon levels. So we can obviously see the difference of levels of 0.2 being 20 chest x-rays per year versus 200 levels, which is the equivalent of more than 60 times non-smoker risk of developing lung cancer from inhaling radon gases. Where can you find radon? Radon is produced by uranium and thorium decaying in the earth and then moving upward towards the surface and then into the open air. Radon is everywhere, but levels depend on how close you are to a uranium/thorium deposit. Why I chose radon? I chose radon as my subject because I live in a house with a basement and a crawl space. And since radon comes from the ground, I wanted to see what the radon levels were in my home, and to see if they could pose a danger to me or my family. Procedure. The procedure I used to collect the data was simple. First, I selected a location to test, which was my basement. After collecting the data in my basement, I set the device in my crawl space and let it sit collecting data for the amount of time it needed. The only control I had on the test were their locations. Data. The observations I made during the testing was depth of the basement and the crawl space. The basement's depth being about 5 feet in the ground, with the radon detector about 1 foot above the basement floor. When moved to the crawl space, which was about 6 inches deeper, the radon detector was dangling only 2 to 3 inches above the crawl space floor. And these are my graphs. So graph on the left depicts the radon levels for the basement, and then the graph on the right depicts the radon levels collected in the crawl space. Data summary. The trends I noticed was that even with only a few inch difference, the data increased noticeably when transferred from the basement to the crawl space. There were no negative spikes in the data. It seemed to continuously increase as the test went on. Scientific explanation. From my data, the only thing that could have influenced my data was on day 1 of testing in the basement. I did have a window open. What I infer from my data is that there is noticeable change in radon levels, even if the change in depth is only roughly 1.5 feet. I do not believe I collected enough data to make a conclusion only because of the short testing period. Areas of error. I cannot find any areas of error. The data was consistent and the procedure was straightforward. The only improvement I can think is a longer testing period to collect more data. And this is my closing statement.
Any questions? Somebody over here? Oh. You don't want the bullfish? Okay.
Were you testing the difference in the depth, or were you testing the difference between the crawl space and the
Pardon, could you repeat that? I was testing to see how the depths did affect the levels of radon in the household.
What about the flooring?
The flooring for the basement had a layer of concrete underneath it with a layer of wood on top of that, and then carpet put over that, so pretty straightforward. And then for the crawl space, it is just basically concrete with a layer of plastic wrap, a very thick layer of plastic put over the floor.
Guys got a question? So if you were to repeat this experiment, what would you do next?
What I would do next to repeat this experiment? Well, for one, I would definitely try to extend the testing period to collect as much data as possible to get an accurate reading on the radon levels in the two areas. But any other differences I could make is I would probably put the radon tester closer to the ground if possible.
Did those two areas that you were testing, the crawl space and the finished basement area, did they have any different ventilation in there? I mean, did you see it there? Is there a difference between the amount of air exchange you might get between the crawl space and the other rest of the basement area?
The ventilation for the basement is just, there is a window and then a couple vents scattered across the floor that sort of bring in and out air if needed, so heating and cooling. And then in the crawl space, there is just basically a giant conduit vent in the center of the room that sucks in air occasionally. I rarely go in my crawl space, so I can't accurately represent what exactly is inside the crawl space.
I'm sorry, we have to cut you off due to time limits. I'm sorry.
It's okay.
Thank you very much. Oh, Miss Williams, we said thanks. Okay.
All right. So.
Hello, my name is Tasha Bradshaw. I'm Katie Brownlow.
Emily Clark.
And I'm Bryn Francovic, and we're with Mr. Taylor's Chemistry 2 class, and we're from Sentinel High School. The question we investigated was, is there a change in PM 2.5 levels with firing different types of firearms?
Background information. PM 2.5 is a particulate pollution with diameter of each particle being less than 2.5 micrometers. Activities such as exercise, pregnancy, stress, and medical problems are an added risk to respiratory problems caused and affected by PM 2.5. Long-term exposure increases the risk for cardiovascular mortality as time increased spent in location with higher pollution. Why did we choose this question? This question was chosen because gun ownership and shooting is important to Montana culture, and the purpose of this investigation was to see if discharging firearms increased the particulate exposure to the shooter.
For our hypothesis, we said that the larger caliber guns should emit more particulate matter because their ammunition contains more gunpowder.
For our materials, we used a wide array of firearms ranging from small caliber semi-automatic handguns to larger caliber bolt action hunting rifles to pump action shotguns. And we also used a Dylos DC 1700 air quality monitor to test our project with.
These are the guns we used.
For our procedure, we went to the Deer Creek Range, which is a private range, and we established a position where we could fire and place a stable, well, we put our Dylos 2.5 monitor on a stable position so we would not have it fall or stop working during our shooting. For the first test, we placed the Dylos 2.5 meter 10 centimeters away from the barrel of the weapon, and for our second test, we placed it a meter away from the barrel of the weapon, and we fired 5 shots per firearm per test. Once our firing position was established, we began our testing, and we continuously tested. So we had data before, after, before, during, and after each shot or in each firearm. To make sure that our data reflected which firearm we shot during which time, we established a time period where we shot each firearm and wrote a list, so we had no ambiguity between the data.
This is a setup of how we tested our weapons. This table shows how we recorded the data and the order in which we shot. The only thing we have to exclude is the .22 rimfire, as it jammed in the beginning of our testing, as you can see. Our graph shows how the different firearms performed. The blue lines separate each of the different firearms, and the high points are the 10 centimeters and the low points are the 1 meter. The only thing that didn't register was the 12 gauge shotgun, did not have a low point, and the .22 rimfire we excluded from our data.
So for our statistical analysis, we use the ANOVA test, which is a test of means as it compares all of the data groups. And our results were that the factor of 1.11 was less than the critical factor of 2.77. Therefore, there was not enough evidence to support our hypothesis. So in conclusion, our hypothesis that larger guns should emit more particulate matter was not supported. The larger calibers did emit more particulate, but it was not statistically significant.
Possible errors that we could have encountered included wind, which could have carried our data to and from our shooting area, and particulate matter from other shooters to our area, which could have interfered with our data. And if we did this again, we would do more tests to try to get more data so we could accurately represent the particulate matter from shooting. Thank you very much. Any questions?
I'm going to ask the obvious question here, and I think we saw on one of the photos. Do you lovely ladies shoot those guns?
Yes.
Yes. All right. Did you have fun?
Yes.
Yes, in the back. For that shooting range, it was pretty average. That shooting range doesn't get too busy. There were, I think, a couple shooters on either side of our testing area, but for the most part, and it was pretty cold that day as well, so that affected our atmospheric conditions a bit. Any other questions?
Any idea how you would try to control outside sort of the shifting winds in that kind of experiment?
The only way we could really control it was by shooting on the same day, so we got the same atmospheric conditions. But other than that, since it's outside and it's a range that people come to often, there's not really too many ways to control that.
And we also did have the option of going into an indoor range, but since there was no like airflow, or not as much airflow as shooting outside, we just went to the outdoor range instead.
Okay, great. It's important to note no animals or children were hurt in the study, so. So I'd just like to acknowledge that we have a very special guest here from Idaho. So a whole nother state is with us again, so from Craigmont, but it's Highland High School in Craigmont, so take it away.
Thank you. Hello, good morning. My name is Morgan Weeks. I am a freshman student at Highland High School, and my project was predicting patterns of indoor radon concentrations in northern Idaho. And so what got me into radon was when I learned that it is the leading cause of lung cancer among non-smokers. And so when I wanted to learn more about radon in our area, I found out the state doesn't really have any testing for our area, so I thought I could change that myself and test some homes myself and see if we could potentially determine what levels of radon are using different factors. And so I had 2 areas of focus I wanted to use. My first one was to just collect as much data as possible to create a body for my area in Idaho. And I didn't want to use that data and see if there was or was not a way we could predict the levels, potential high levels of radon using the underlying geology. And so what we have here is the raw data. I have 12 sites tested, and of those 12 sites, there were 2 geologic areas. There was a QTPMS, which was a sedimentary area, and then there was a KJQD, which is a quartz diorite area, which is igneous rock. And so here is my map right here. As you can see, this is Craigmont, Idaho, and then all the rest of the data points were within a 15-mile radius of that. And as you can see here in the darker shaded stuff is the sedimentary rock, and the lighter shaded stuff, such as here or here and here, was the igneous rock. So this is a chart based on the geologic type. I have on the first column the site numbers, and in the second column I have the geologic type, and in the third column I have the radon reading, ranging from 0.9 to 7.7. And my total average of those readings was 3.7. Picocuries per liter, that is. And then my average of the igneous rock was 3.4, and my average of the sedimentary rock was 3.9. I found this interesting because I expected the igneous to be higher because it tends to have more uranium in it than sedimentary. But I think due to the lack of volume in my data, there wasn't really a statistically significant difference that we can find out. And so here's a chart of my graph. On the x-axis, we have the site numbers, 1 through 12. And on the y-axis, we have the radon levels in picocuries per liter ranging from 0 to 9. And of my 12 sites, 4 out of the 12 sites were above the EPA recommended level of 4.0. And then here's the same chart, but based on the geology. As you can see, the green triangles are the sedimentary rocks, and the blue diamonds are the igneous rocks. And then on the y-axis again is the radon level in picocuries per liter. And in conclusion, I had troubles collecting data, mostly because of the turnaround time. Radon takes about 48 hours to collect data, so best case scenario, I would receive data every 3 to 4 days and then hand it out and receive it again on a cycle like that. But on most occasions, it took 3 to 4 weeks to get back my radon from volunteers. And I go to a really small high school. There's under 50 students in the high school, so the lack of volunteers really hurt me. However, I did address my first problem, which to successfully add Craigmont data. And to address my second problem, I will need more data points to see if there is a statistically significant difference. And then implications for future research include to collect additional data, to then use that data and see if there is a geologic pattern, and then later maybe retest some homes in different seasons to see if there is any patterns related to the seasonal conditions, like as opposed to winter over summer. And then what would you like to see? Yes.
What procedure did you use to help limit variables between your testing sites?
I gave each of the test subjects a radon test kit, and then I gave them a set of instructions too that were exactly the same. And it was in the basement, and then it had the fall thing that I got from online from a source. Yes.
Why didn't you test equal number of both geological types?
Excuse me?
Why didn't you test an equal number of both geological types?
Mostly because, as I said earlier, there wasn't really much for volunteers, and I couldn't really pick. It was just random. Whoever would take it would really get me data. Thank you.
Questions? Right.
My name is Kelsey Fox. I'm from Moody High School, and my teacher is Mr. Gene Reckon. My project was on the effect of firewood moisture content on indoor PM2.5 emissions from wood stoves. My purpose was to measure the effect of firewood moisture content on indoor PM2.5 emissions from wood stoves. It's recommended by the EPA to burn below 20% moisture content. My hypothesis was as moisture content increases, I expect PM2.5 to increase. It was a 24-hour testing period. I placed the Dialos monitor about 5 feet away from my wood stove. I tested larch and removed the bark because there's no way to test moisture content in bark. I tested 6, 9, 15, and 20% moisture content, and 6% was about as dry as I could get the larch to go, and anything over 20% has a difficult time burning. I used kindling of the same moisture content for each test too. To find moisture content in the wood, I used a Delmore's J-Lite wood moisture meter, and it measures the moisture content by the conductivity between each electrode, which these are the 2 electrodes, and it works by pressing the 2 electrodes into the wood with the grain, and it gives you a LED reading ranging from 6 to 30%. I used approximately the same volume of wood for each test, and the wood stove was stoked periodically just to maintain constant home temperature. The humidity remained around 25%, which I used a general hygrometer to measure humidity in my home. This is a graph of the maximum and minimum values. 6% is right here, 9, 15, and 20. 6% peaked at 24 micrograms per cubic meter, while 20% peaked at 213, which is above the EPA recommended micrograms per cubic meter for particulate matter. And this is a graph of my average values. 6% averaged at 0.45 micrograms per cubic meter, and 20% averaged at 154. And 9 and 15% were relatively close the entire time. It would help to get a extra data point between 9 and 15 to explain why they were so close. My data showed significant support for my hypothesis, and it just goes to show how important indoor air quality is. There's outdoor regulations for outdoor air quality, but what about indoor? You spend most of your time indoors during the winter, and if you have wood heat, you're being exposed to that particulate matter. So, possible PM2.5 disturbing activities were kept to a minimum, such as cooking or cleaning, but nonetheless could have led to potential error in my project. And for further study, I would like to try a wider range of moisture content, such as the halfway between 9 and 15% moisture content. I would also like to try a different wood species to see if it would give me different readings. To conclude, burn and dry firewood. Any questions? Yeah.
How do you change the moisture content between?
I basically just, I set it the 6% in my house to try and dry it out, and then just tested it every couple days. And the 20% I was sitting outside for a year, so it was pretty saturated. Any more questions? Yeah.
I didn't hear where you were putting the monitor in the study. Did you say that?
It was 5 feet away on a stool, 5 feet away from my wood stove on a stool.
Okay.
This high.
So like wasn't at the ceiling?
No, it wasn't. It was about that same height as the wood stove. Anyone? Yeah.
Moisture content can vary throughout the logs. How would you take your moisture readings?
The manual for the J-Lite wood moisture meter that I had just said to stick it in with the grain, and I assumed that it would measure throughout the entire log. Yeah.
What do you think the mechanism is that causes more human wood to burn and give off higher particulate?
With more moisture content in the logs, combustion will complete, so you'll get a higher particulate matter in your smoke, I assume. Thank you.
Okay.
Hello, my name is Alyssa Penrose.
I'm Sierra Pinnell.
And I'm Winnie Law. And we're from Sentinel High School Chemistry 2 class, and our advisor is Brett Taylor. And our project was comparing the PM 2.5 levels found in different aerosol and non-aerosol hairspray. Our question was, is there a difference in the PM 2.5 levels associated with various hairsprays?
So some background information that we found is that hairsprays contain many ingredients, and some of them being solvents of alcohol and hydrocarbons. And we found that these solvents have a lot of harmful effects, some of them being kidney and liver damage. And we also found that kids are more vulnerable to these types of air pollutions.
Our hypothesis was that the PM 2.5 levels would be dependent on the cost of the hairspray, because the more ingredients that it has would determine the particulate level.
For our location, we chose the Sentinel Drama Department's girls' dressing room. It's a small space where people often use hairspray and there isn't much ventilation. The reason we chose this location was because both Sierra and I are actively involved in our drama department, and we wanted to see what effects hairspray could have on us and others. For our materials, we used the DC 1700 air quality monitor, Pantene aerosol and non-aerosol hairspray, which costs $3 to $4, and White Rain aerosol and non-aerosol hairspray, which costs $1 to $2.50. For our process, we let the monitor sit in the room for 5 minutes to establish a baseline. We then marked with tape 2 meters away from the monitor and sprayed the hairsprays for 10 seconds. We then let the hairspray sit for 5 minutes. After those 5 minutes, we turned on the fan and opened the doors to let it fan out for a few minutes. We would then repeat this for each hairspray.
So here we have some photos. Our first one is the fan that we use to clear out the room in between each test. We have a picture of the monitor sitting on the chair that we used, and then both me and Sierra doing the hairspray tests.
So this is our data, and as you can see, these numbers correspond with the numbers on the side. So this first one is where we sprayed the Pantene aerosol hairspray, and this is where we first sprayed it, and then after the 5 minutes it spiked to here. This is our second hairspray, which is the Pantene non-aerosol, our third, which is the White Rain aerosol, and the fourth, which is the White Rain non-aerosol. So as you can see, there's obvious peaks in the data. However, we did a combination of t-tests with all the hairsprays, and we found p-values ranging from 0.22 to 0.39, and at that alpha level of 0.05, there's not enough evidence to conclude that there's statistical difference in the PM 2.5 levels with these types of hairsprays. Yes, Pam.
So before testing each hairspray, did you let it down to baseline?
Yeah, so we would spray it, and then after the 5 minutes, we'd fan out the room, and then we'd let it sit, and then we'd do it again.
You regulate the amount of hairspray coming out between aerosol and non-aerosol?
So we just spray the hairspray like you would normally spray your hair. So we would do it like that motion, I guess. So we would just spray it like you're actually spraying your hair.
Wouldn't there be a lot more coming out of aerosol?
Well, okay, you're answering.
With the non-aerosol hairspray, we just consistently squirted it for 10 seconds, I believe.
Yes.
So how many tests did you run for a hairspray?
So we actually only did it one time, which is one of our things. If we did repeat this process, we would do more tests, and we would spray it multiple times.
So after you apply the hairspray, does the person who applied the hairspray stay in the room while you use the 5 minutes or however long?
Well, we use the fan to like air it out, so I'm guessing some of the hairspray probably stayed behind, but we tried to get the majority of it out of the room.
Going back to another point is when you were airing out the room, what were the values between, and at the very beginning of your test, so before you did run number 1, and what was the value between run number 1 and 2? How good was your airing out, basically?
We like aired out the room for about the same time. There was no way for us to like get it exactly to the baseline. We kind of just measured the like difference in like from when it started out and when we sprayed it to its peak.
All right, thank you.
All right, so how many of you guys have cats in your household? Can I just get a quick poll, raise your hands? Wow, more than I expected. Well, in that case, this is for you. I'm Michael Sorensen, that's Chelsea Diaz, and that's Vance Sebastian Reed. And today we are going to present how kitty litter actually affects the air quality. As you can see, we're the more comical side of chemistry. So our hypothesis, we believe that changing the litter for litter boxes skyrockets the PM 2.5 to unhealthy levels, and the chemicals produced by the litter are even more unhealthy. So the questions that we aim to answer for all you curious kitties out there is kitty litter significant? Is kitty litter significantly harmful to air quality, and if so, how could this affect people?
So I'm going to talk about some of the harmful ingredients in kitty litter. First off, I'm going to start with sodium bentonite clay. Now, it's cheap and we use it a lot and it's not good for you, which sounds like a lot of things we have. So the thing about sodium bentonite clay is that it has high levels of sodium ions, which is way more than its calcium counterpart. Now, why is this bad for us? Well, when you have your face in kitty litter scooping out things, it gets right in your face, it gets in your lungs, and it starts to attack the mucous membranes. It wants moisture. It wants it to clump and be in a pretty little package for you. Well, when that gets in your lungs, it starts to attack the mucous membranes and can cause respiratory problems. Silica gel, which is also cheap, and you can find it in your beef jerky and new shoes. When you get that in your lungs too, it's classified as a human carcinogenic. Yet it's still used in 95% of kitty litters. So,
adorable.
Our procedure. Over a period of 4 days, we changed the cat litter 7 times, once on the first day and 2 times on the other 3 days. So our constants, we did it relatively the same time each day. We used a handheld scooper. No windows were opened, fireplace was not used, and the dilose was placed on a swivel chair right next to the kitty litter box so you can mimic that hand scooping action. And that's the kitty litter we used. So, our data for day 1. That's the room we used. That's a quick picture. We have 2 others. This kind of shows as time progresses. This is during the night. This was our first litter change. As you can see, we had a small spike. And we have the EPA 24-hour standard, which is at the top. So it's not dangerous quite yet.
Yet.
Alrighty, and as you can see for our day 2, we changed it twice. Once at 7:55 a.m. and the second time at 6:20 p.m. And as you'll notice, the first spike, it jumps quite a bit up there to about 60 p.m. 2.5. And the second time it jumps all the way up to around 120, which is well above the EPA 24-hour standard. The third day was relatively the same as the second, except our first change at 8:02 a.m. jumped around 70, and our second change as well jumped around 70, which is still quite a bit above the EPA standard. And on the last day we did it, it didn't seem to jump quite as high. Our 2 changes were a little closer together, once at 5:47 p.m. and the second time at 10 p.m., but we can still see that the time between it went back down to base. So in conclusion, sifting through litter twice daily, cleaning, increases the PM 2.5 count on average 30 times its normal count. The spikes are huge and they only last for about 2 minutes.
So we don't really have any solutions, but we have some theories. One of them being don't have indoor cats and you won't have litter. Our second theory being get an automatic kitty litter box. Now this may not help improve those spikes, but it also limits the direct human contact. Your face isn't in it, it's not getting directly in there. So some things we could have fixed. Obviously, we could have tested different kitty litters, and we did it for 4 continuous days straight. We could have done it for longer, perhaps different weeks, just in case there was different air quality within the house. And then we have our sources. So, do we have any questions? Yes.
I was curious, the first scoop that you guys did that was under the threshold, what do you attribute that to?
Well, one of the things we attribute that to is it was in my house. We have a bathroom door that has our whole ventilation system in the bathroom. So if the door shut at night when the heater comes on, there's a huge draft. And our first litter change was at 9:27 p.m. So I wasn't paying attention to the bathroom door, so I assume that could be one of the contributing factors. It pushes a lot of air out of there. So, any other questions? Yes.
So in the beginning you mentioned the 2 different ingredients that they could have in the cat litter. Which kind did you use, or did you use both?
Oh, those are that's what the kitty litter is made out of. Those are the 2 main ingredients. It's commonly found in, like I said, 95% of kitty litters. So,
All right.
yes.
Was the cat using the box in this?
Yeah. Yes, it was.
You were actually.
I was actually, yeah, it wasn't fun. Anyways. Any other questions? Yes.
Why is it, so you're using the same scoop and the same litter every day?
Mhm.
Why is it like that one, like on the second day, it goes way above, but then on day 3, day 4, it keeps going back down? Why is it?
Day 2 and day 3, day 2, day 3, and day 4, we had relatively the same amount of spikes. Day 1 was the only one that was really different. And day 2, day 3, day 4, they spiked way past our grid. It went actually past our graph just for the sake of getting them in there. We zoomed it in. So, anything else? Yes.
What do you recommend, or do active ingredients bad in cats too? Are the active ingredients bad in cats too?
Oh yeah, when the cats ingest the litter, it causes insoluble masses in their body, and it prevents them from absorbing nutrients effectively.
So that's why my cat coughs a lot. The more you know.
Okay, so I think we're done with questions. Thank you.
All right. I'm Skylar. This is Spencer. This is Ronnie, and this is Dylan. Our project is on, well, instead of physical health problems you get from bad air quality, let's say they tested the air quality in track and baseball and tennis or swimming. That's usually what people think of as bad air quality. Well, yeah, you're gonna have physical health problems, but we're testing the mental health problems of bad air quality, as far as suicide, on if it could affect the rates of suicide in certain areas. So our hypothesis is the higher the PM 2.5, the higher the chance of suicide in certain areas. Okay, so the purpose of the experiment is to test if air pollutants have an effect on your brain that can lead to increased suicide risk.
Alright, so some background information. Utah did a study on air quality and how it affects the suicide rates. And in that study, they were looking at the levels of nitrogen dioxide and how it affected people. And they found that victims in the Salt Lake Valley, there was a 20% increase of suicides for those that were exposed to nitrogen dioxide. And they also found that there was a 5% increase of those that were exposed to a PM 2.5 level particulate matter. And in Montana, Montana is the second highest state in the nation in number of suicides per 100,000 people. it has 20.5 suicides. And for our study is not to, it doesn't prove that air pollution causes someone to commit suicide, but it suggests that the higher levels of PM 2.5 might interact with other factors to increase the risk. For our procedure, we emailed this IT girl from the Missoula Sheriff's Department, and the sheriff gave us confirmation, and he gave us the data for the number of suicides that happened in Missoula County from 2011 to 2014. And then after we obtained the data, we went to the montana.gov website and found the PM 2.5 levels on all 3 days before someone committed suicide. And we took those levels and made a mean average and made graphs.
So what this is showing is on the top is whole 2013 air quality, which is about a typical year. Winter wood stoves will spike it up, and then spring is pretty good for air quality. Summer fires will spike it up, and then fall, just like pollens and stuff can increase it. And then what I did is on the bottom is suicides by month from 2011 to 2014. And what this is showing is if you look in the block from February to May is when about most of the suicides happen, May and June and spring, but that's when the best air quality was. So we actually found the exact opposite of what Utah found. We found that during the best air quality is when the most suicides happen. So we believe it may be more of a season type of deal, not really that it affects you. And then we performed a t-test, a two-tailed t-test, and we found that a p-value of 0.0086, which is considered to be very statistically significant. So I mean, our data is not the same. It's very, very good, but they're not the same thing. And there's actually a big difference on suicide. So we took the 3 days before they committed suicide, and the air quality is actually better. It's 7.73 micrograms per meter cubed on those days than it was the non-suicide days.
So in conclusion, on most days prior to the suicides, there was like better air quality. So this refutes the results from that the Utah study found. Then some improvements that we would have liked to have done better. We could have got like more information from more cities in Montana so we can compare results. And then test if like different gases in there have effects on your brain and suicide. And that's it.
Any questions?
Any questions? Okay.
Thank you. Is there one up there?
Yeah.
Was there a question?
Got one question.
Oh, okay, question.
How many suicides were there?
I think, let me go back. In total, there's about, I think there's between 2011 and 2014, there's a total 124 suicides in Missoula. This is all data from Missoula. Any other questions? Yes.
Why do you think your experiment was different than that of the Utah study?
Well, we're trying to see, because Utah is really one of the only places that has done this study, but we want to see if we could back up their information. We're seeing if our evidence found the same thing, because like he said in background info, Utah had a lot. They found that it was increased, but with ours, we found that it's not, that in the springtime when the air quality is best is actually when there's the least amount of suicides, or the greater amount of suicides, I mean, sorry. Yes?
So did you guys get your PM 2.5 like readings as an average of like that day in Missoula County?
Well, yeah, so we went to that Montana.gov, and then we just went through from on every single day from 2011 to 2014 and found the air quality, and then we separated the 3 days out of before and the day of the suicide, and then we found the average of both of those. Yeah.
So how did your study or the Utah study try and like
separate correlation and causation? How do you know that the air quality had any impact?
Utah's air quality is one of the smoggier cities that we know, and it's got a lot more people and a lot more cars or industries than Missoula does, so that could affect a lot of the results that we got.
So the air quality on average during the, between 2001 and 2014, for the months, were they about the same on average?
Yes, they're pretty much the same. Montana is one of the cleanest states in the nation, so it stayed roughly the same.
Yeah, that's why we picked 2013 just to graph it, because it's just showed the typical year of air quality. Any more?
Why did you choose Missoula?
Sorry.
Sorry, go ahead and answer the question. Why did you choose Missoula?
It's close to, I mean, we're in Missoula right now, you know, it's just interesting to see. Like we said, it'd be interesting if we did this study again, if we could have gotten more cities and say Bozeman or in Billings and kind of compare all of it. Missoula's just, I got a hold of them, and it's just a good place because we're close.
All right, thank you.
Thank you.
Hi, I'm Spencer Mueller.
Hi, I'm Dalton Thick.
And I'm Jake Salyers. And our project was PM 2.5 levels associated with cleaning large caliber rifles, and we're from Sentinel High School, and our advisor is Mr. Taylor.
Our question was, does the number of shots fired from a hunting rifle affect the PM 2.5 levels when cleaning the rifle?
So PM 2.5 is particulate matter that has a diameter of 2.5 microns or less. Some health effects include asthma, COPD, and allergies. And the purpose is to determine if there's a relationship between PM 2.5 levels and the number of shots fired when cleaning a rifle. And we chose this topic because each of us are avid shooters and wanted to determine if there's the air quality is impacted by cleaning the guns.
So our hypothesis was if the number of shots fired from a 30-06 and a 270 are increased, then there will be a corresponding increase in PM 2.5 levels when cleaning the rifles.
So for our procedure, we went to a gun range and we fired 130 grain bullets from both the 270 and the 30-06. And when we were cleaning the rifles, we measured the particulate matter using a DC 1700 air quality monitor, which was 1 meter off the ground and about 38 centimeters away from the muzzle of the gun. And for our control, we cleaned a clean gun. And after we shot 1 shot, 2 shot, 3 shots, 5 shots and 10 shots, we cleaned the gun each time by sending a brush down first, followed by a 2 by 2 inch pad with Remington oil on the first patch, and then we sent 6 more patches down. And then after recording the amount, we cleaned the gun the rest of the way, so we had our baseline.
So this is the graph A, so the 30-06. And so first off, this is our, just keep talking. Okay, so this first part right here, that is cleaning a clean gun. Then that was after 1 shot, and then that was cleaning after 2 shots, cleaning after 3 shots, and then 5 shots, and then 10 shots.
So each shot group, they each created a spike in PM 2.5 levels, and then after 3 shots, they each reached a maximum level.
So this is the graph of the 270. We had our baseline, and then that's after 1 shot, after 2 shots, after 3 shots, and then 5 shots. And unfortunately for the 270, we didn't get the 10 shots because right as we were cleaning it, a truck drove up.
So the shot groups 1 through 3 are similar, and then after 5 shots, there was a jump in PM 2.5, and at 10 shots, a diesel truck drove up, and the data was invalid.
So for our statistical test, we did an ANOVA single factor statistical test. Our F factor was 1.097. Our F factor critical was 5.05. And since F is less than F critical, there's no statistical difference between the number of shots fired and the PM 2.5 levels when cleaning a gun. So it doesn't support our hypothesis.
So So in conclusion, PM 2.5 levels associated with cleaning high caliber rifles is not significantly affected by the number of shots fired.
Questions?
So is rifle cleaning then overall contribute to air quality?
No, because it doesn't produce that very much small particulate matter.
Except for one rifle.
So that would probably be what we could do if we were going to expand our experiment. We could do more rifles like an AR-15 or a 223 or a 22, and then maybe compare the data of those to the ones that we gathered here today.
So how many rifles in the Western Army have?
What'd you say? I couldn't hear you.
How many rifles in the Western Army?
How many rifles?
Rifles in Western Montana. A lot.
How many calls on it?
Well, just on average, like to keep a gun in good working condition. A friend I know, he's really big into shooting, and he says they have to put at least 50 rounds through a gun like every month to keep it in good condition. So I'd say that there's a lot of shooting in Montana, and if it does affect the air quality, it's not a whole lot.
All right, thank you. All right, so I think that is all of the presentations. Did I skip anybody? Anybody want to give theirs over? Okay, so now we are going to give away or recognize some of the judges for the posters and the presentations real fast, and then we are going to go have some lunch, and then we're going to come back in here and give away some prizes. So first off, let's recognize our poster judges, so the folks that have their posters next door. And during lunch, if you get an opportunity, go check out the posters next door. There's some really good ones this year. So first person we'd like to recognize is Carolyn Hester. And then Emily Weiler. Emily's a Big Sky grad from way long time ago. And then Matt Ferguson. We'd also like to recognize a couple of students that have been helping us out all day. So Jed Sireni. And then also Kyle Brester. And then we'd like to recognize our judges too. So first off is Ben Schmidt. Aaron Yost. Ashley McGrath. Ian Foster. And Mary French. Okay, thanks for the judges for taking time out of your day to judge the presentations and the posters, and we certainly appreciate it, so thank you. Okay, we're going to go ahead and get started again. Thanks for coming back so much. So right now we're going to give away some certificates, and this is Dr. Earl Adams from the Department of Chemistry here on campus, and Earl is going to make the announcements.
Okay. All right, we just kind of first, before we get started with the awards, we want to kind of give some recognition to our teachers who led you guys and mentored you guys through this. If we would, could the teachers stand up here for a few minutes? High School. Mary Rimpey from Highland High School, Idaho. And Dave Jones from Big Sky High School. Big round of applause.
This is Mr. Reckon's last symposium. He's retiring this year. So Mr. Reckon has been coming for many years now to the symposium and has been teaching for 35 years. So I'd just like to especially recognize Mr. Reckon. Thank you very much, Mr. Reckon.
I know also you should one of those groups that those are meant to be handed to you too. Okay, let's see. Ready, teachers? 1, 2, 3, smile. Wait, let me back on you. Let's try again. 1, 2, 3, smile. All right. Okay, grab a mug. You get a mug too, right?
Presentations and posters. We have Dr. Lisa Blank from our School of Education that's going to talk about evaluation programs.
Just like you have to evaluate your projects for this semester, my job is to evaluate the grant and the funding that comes to support all the work that you've been doing here. So it's really important that we get feedback from you on what's working, how it's working, and what your suggestions are. So in the moment, what I'm going to do is pass out to you an evaluation. There is no right or wrong answers, but certainly the most authentic, honest answers that are complete are the most helpful if you want to help continue our improvement of your project. That's how we'll use this feedback, is to form our own process, just like we use your own data. So you have 15 minutes to do this. When you are done, what I would like to do is turn it over upside down and just give me a thumbs up so I know to come back and pick it up. It is completely confidential, so there is no way that anyone will see it besides me. So without further ado, I'm going to pass it out. And remember to turn over when you're done. Keep your hands up, thumbs up rather, and I'll come by and pick it up. Thank you.
All right, first, thank you for your attention, please, for just a quick moment. This is my last event here, so I get the mic for a couple minutes, so I'm going to let it rip here. What I'd really like to do is just suggest an incredible thank you to all of these people here who put this on every year. We people who live in rural America have a tough time, and for a lot of our kids to have an opportunity to come to the university and see what a place like this is like, participate in a scientific endeavor like this, it is just so meaningful for our kids. So a huge thank you to Tony and to Earl and Desiree and Naomi and Diana and Carolyn, the whole lineup here. These people are wonderful. Whenever we call with problems, they're just on it. We're FaceTiming now, and we get to see you in full color too, even remotely. But it's just wonderful. They've been so supportive and so helpful, and have really opened a lot of doors for our kids. It put some of our kids to work here who participated in this project. And we were students then. They got to come here and actually get to work in the labs and whatnot. It's just been a delightful experience, and we are eternally grateful for all you guys have done for us. So thanks a million.
All right, with that said, let's give away some awards. So Carolyn, I think you have the poster awards.
Oh, I'm not. I wasn't done. Oh. Thanks to Dave Jones, who kind of got this whole thing started here about a dozen years ago or so, with a student or maybe just one that wanted to do some kind of project here, and this whole thing kind of mushroomed from that. So I think he was kind of part of the brainchild here, got it going, so big thanks to Dave.
Well, I first of all would like to thank all the students that put a poster together. The posters really reflected all the energy we put in, all the hard work and research, and also creativity. It was definitely a difficult decision when we decided who would win first, second, or third. But we did come to a decision. So the third place winners, their poster was called The Effects of Vacuuming and Air Quality in the Home, from Corvallis, Molly Dubose, and Sarah Jessup. All right, second, the title, Carbon Monoxide Emissions of Different Types of Autos, Cheyenne Shywick and Lindsay Hartz.
Yeah, maybe this.
Trying, not working, just kidding. Turn the camera on. Okay.
Okay, and the first place winner, comparing the air quality of different methods of cooking popcorn. Janae Mitchell, Shayla Palmer, and Shelby Toe.
Nice job, Mavis. There you go.
Okay, and before we, congratulations to the poster winners. Before we give away the final prizes for the presentations, we'd just like to thank a couple people in the audience. So one is Montana DQ, especially Bonnie Rouse, who funds the program every single year. So Bonnie, go ahead and raise your hand. Thank you, Bonnie. And also the National Institute of Health has a Science Education Partnership Award who funds this program as well. So with that said, here we go with the presentation.
All right, I'm going to yell these out. Third place PowerPoint presentation, the effects of firewood moisture content on indoor PM 2.5 emissions from wood stoves, Kelsey Fox from Libby High School.
I'm in the background. It's like ruins the picture.
I'm here today.
Okay, second place, radon mitigation barriers in basements and crawl spaces, Aria Benefield and Isaac Jones from Libby High School.
Congratulations. Congratulations. You guys have to get your picture. It's not optional. Thanks.
Nice job, guys.
Congratulations.
And finally, first place, air quality and indoor swimming facilities.
You're on the outside. All right, and with that, I think that we are done. Thank you very much.